Hello everybody, welcome into another lesson. So today we are going to talk about a very common application that you will find in Algebra 2 and in pre-calculus, and also if you go into accounting or the business or finance fields, is compound interest. This really applies the idea of exponential functions. So here we have two formulas for compound interest. Up till now, you've probably seen the simple interest formula where you have I equals PRT. Well, we're going to talk about compound interest. Both of these formulas apply exponential functions. So A is the amount you'll have in your account after a certain time period. That for general compound interest, it's equal to P, which the P is the principal. It's the amount that you initially invest or deposit, times the quantity of 1 plus R over N, where R is the rate, it's a percentage rate, over N, which will be the number of compoundings on the account. All that raised to the nt power, where n again is the number of compoundings and t is the time given in years. First, we'll talk about the general compound interest formula. So we have a problem here where Sam deposits $5,000 into an account with 8.5% interest for 1 year, compounding annually. Find the amount of money Sam has after 1 year. Okay, so here's how you got to approach this. So we want to find the amount he's going to have after 1 year with one compounding. So A, of course. Now let's read the problem. Sam deposits $5,000 into an account. So the principal is $5,000. That's what he's initially investing. So that's going to, of course, be $5,000 for the P. That goes where the P goes, times the quantity of 1 plus, now we got to find the rate, that R. It has 8.5% interest. Well, when you do the rate, you got to express it as a decimal. What is 8.5% as a decimal? It's 0.085, right? So plus 0.085 divided by the number of compoundings. How many times does it compound? It compounds annually, meaning once a year. So it's only going to compound once in a year. So you'll divide that by 1 for one compounding raised to the nt power. Again, it compounds annually, so that would be to the 1 times, and then for 1 year this compounds to the 1 times 1 power. So we can simplify both the parentheses and the exponents. This would be equal to $5,000 times literally 1 plus 0.085 to the 1 times 1 power. That's just to the first power. So that's going to equal $5,000 times 1.085. And then we should get a decimal approximation here about how much you'll have after 1 year. So let's go ahead and take that, okay? So 5,000 times 1.085, that would give him about $5,425. So Sam would have roughly, actually he'd have exactly $5,425 if this compounded annually at 8.5% interest for 1 year. So he would gain $425 out of just letting his money sit in that account for a year. And of course that's going to increase if he left it in there for 2 years, for 3 years, or so on. Now, what if we modify this slightly? let's modify this slightly here. Let's modify the problem. So let's see. It's going to be the same amount he's putting in at 8.5% interest for 1 year, but it's going to compound semi-annually. This time the interest will compound semi-annually. So let's set this up again. So the amount he's going to have after 1 year, of course the principal is $5,000. He's depositing $5,000, right? Times that quantity of 1 plus the rate of 8.5%, which is 0.085 as a decimal. Now, what are the number of compoundings? It compounds semi-annually. That means every 6 months. So there's going to be 2 compoundings that year. So this is actually going to compound twice in 1 year. This is going to be raised to the nth power. Well, the number of compoundings, again, is 2 this time. This is actually going to be to the second times the t for 1 year. So let's simplify this a bit here. That's going to equal 5,000 times, let's see, 1 plus, let's find 0.085 divided by 2. So we'll simplify this a little bit here. 0.085 divided by 2 is exactly 0.0425. Raised to the 2 times 1 power, that would just be raised to the second power, which would then mean that we have $5,000 times 1.0425 raised to the second power, which will give us an approximation here. So let's take that 1.0425 to the second power. And then we'll take that times 5,000. So he would have $5,434.03 roughly. So if he left that $5,000 in the account for 1 year, but the interest compounds twice in a year, at the end of the year he'll have $5,434.03. Okay. Now, we're going to change the problem again. So he doesn't gain terribly much more than once a year, but it's like $9 and some change more. Alright. Now, we're going to keep the amount he's investing the same and the percentage rate of interest the same for the same amount of time, but this time the interest will compound quarterly. So Sam deposits $5,000 into an account with 8.5% interest for 1 year, compounding quarterly. Find the amount of money Sam has after 1 year. So quarterly, there are 4 quarters in a year, right? That would mean every 3 months it's going to compound. So the initial amount, the principal, that hasn't changed. That's still $5,000. Now that's going to be times 1 plus that rate of 8.5%, which is 0.085. Now quarterly means how many times in a year does it compound? It compounds 4 times. This is going to be raised to the nth power. Well, that n is the number of compoundings per year, so that's 4 compoundings per year times the t, which is 1 year. Alright, so this will simplify into $5,000 times 1 plus, let's figure out what 0.085 divided by 4 is. Zero point 0.02125. And then that 4 to the 1 to the 4 times 1 powers to the 4th power, which will simplify this into $5,000 times 1.02125 to the 4th power. And now we can proceed to get a decimal approximation. So you're probably starting to see how this is going to work. 1.02125 raised to the 4th, so we'll take that times 5,000. That would be $5,438 and roughly 74 cents. So if Sam leaves that $5,000 in this account with 8.5% interest for a year and it compounds quarterly, at the end of the year he'll have $5,438.74. Alright, let's change it again. Alright, this time it's going to compound monthly. So Sam deposits $5,000 into an account with 8.5% interest for 1 year, compounding monthly. Find the amount of money Sam has after 1 year. So there's a monthly compounding of interest. So let's go ahead here. Of course, the amount is going to be the principal, which is that $5,000 he deposited, times that 1 plus the rate is 8.5%, so that'd be 0.085 divided by the number of compoundings. Well, if it compounds monthly, that means there are 12 compoundings in the year. Then again, the NT, that ends the number of compounding, so this will be to the 12 times the T, which is 1 year. So we can simplify this now. You'll have 5,000 times 1 plus, let's figure out what 0.085 divided by 12 is. It is going to be, let's see, let's round to 5 decimal places. So 0.00708, it's roughly that. Then to the 12 times 1 power, which would be to the 12th power. Now, of course, this will simplify into $5,000 times 1.00708 raised to the 12th power, which now we can get a decimal approximation. 1.00708 raised to the 12th power, so we get that times 5,000. Alright, so you have roughly after a year, Sam would have rather $5,441.74. So if the interest compounds monthly for 1 year, after 1 year, Sam will have $5,441.74, roughly speaking. All right. Let's change this again, the number of compoundings. This time, the interest will compound weekly. So we have weekly compounding interest. So Sam deposits $5,000 into an account with 8.5% interest for 1 year, compounding weekly. Find the amount of money Sam has after 1 year. So again, the amount he's going to have is the principal, that P, which is $5,000, times that 1 plus that rate of 8.5%, which is 0.0885, excuse me. I don't know where I got the 25 from. Divided by your number of compoundings. If it compounds weekly, how much is that in a year? That'd be 52 roughly. We'd say 52 compoundings because that's about how many weeks are in a year. To the NT, well, again, 52 compoundings in a year, if it's weekly, times for 1 year. All right, let's simplify this here. So you'd have $5,000 times, let's see, 1 plus, let's figure out what that awful decimal is. 0.085 divided by 52. Let's round it to 5 decimal places again. 0.00163 to the 52 times 1 power, that's to the 52nd power, which would simplify this into 5,000 times 1.00163 raised to the 52nd power, which now we can get a decimal approximation if it compounds weekly. All right, so 1.00163 to the 52nd power is that times 5,000, which would give you roughly $5,441.90. So after 1 year of weekly compounding interest, Sam would have roughly $5,441.90. And now let's get into one more variation of the regular compound interest formula, which would be daily. Let's take the interest compounded daily. That might help. Let's do that. See what that's going to look like. All right, the interest is going to compound daily. So Sam deposits $5,000 into an account with 8.5% interest for 1 year, compounding daily. Find the amount of money Sam has after 1 year. So yes, in a leap year there's 366 days, but for normal purposes we'll assume the year's 365 days, a normal year. So after 1 year, let's see, the principal hasn't changed. That's still $5,000 times that 1 plus that rate of 8.5%, which would be 0.085, divided by the number of compoundings. Well, if it compounds daily, that's 365 compoundings in the year. All that raised to the NT power. With the number of compoundings, that's 365 times the time in years is 1 year. So let's simplify this a bit. You would get 5,000 times, let's see, 1 plus whatever that is for that decimal. It's not going to be pretty. 0.085 divided by 365 would give you approximately 0.00023. And then to the 365 times 1 power, that'd just be to the 365th power. So let's simplify this further. That's going to give you $5,000 times 1.00023 to the 365th power. And now we can come up with roughly a decimal approximation of that. Alright, so 1.00023 to the 365th power times 5,000. So actually, we're making less. So $5,437.82. Sometimes this goes to show that the longer you leave it, or the number of compoundings does not always increase it. So actually, you would make less than if it were compounded, weekly. $5,437 and then 82 cents is what he would have after 1 year if it were compounded daily. Alright, so that's the simple compound interest formula. Now, let's go into continuously compounded interest. So, Sam deposits $5,000 into an account with 8.5% interest for 1 year, compounding continuously. Find the amount of money Sam has after 1 year. So it's compounding continuously. So from start to finish for that whole year, it never stops compounding, not even for a second. There is a different formula for continuous compounding. That is A equals PE to the RT power, the PERT formula. So the A is still the amount you'll have after the given time, where P is your principal that you invest. Then you have that number E that we talked about last lesson. You're starting to see where E comes into play. It's all about continuity. And then to the RT, that R again is the interest rate, it's the rate, and then T is for the time in years. So let's set up the problem here, okay? Sam initially again invested $5,000, right? Now this is times E, you have that default E to the RT, so it's 8.5% interest, right? So this is going to be to the 0.085, because that's the rate in terms of a decimal, times time for 1 year. Okay? So of course, then we can get a decimal approximation for what he'll have if it's compounded continuously after 1 year. So let's take E to the 0.085. You'll get that times 5,000. Now that's much better. You'll get $5,443.59, roughly speaking. So after 1 year, if this interest compounds continuously, then he'll have $5,443.59. Now, this time, we're going to say it compounds continuously. He's only going to leave his money in there 6 months. So let's leave the money in there for 6 months and let it compound continuously. So Sam deposits $5,000 into an account with 8.5% interest compounding for 6 months. Compounding continuously. Find the amount of money Sam has after 6 months. So, again, your amount is your initial principal, which is $5,000, right? And then you have that E, and your rate, of course, is 0.085. Now, what's your time? The T is always in years. So what's 6 months? 6 months is half a year, right? Or we could say to 0.5. So that's 0.5 years is 6 months. So now we can get a decimal approximation if you put all this into your calculator. And you see this is a much simpler formula to work with. So if he leaves it in there 6 months, he's still doing all right. He'll have $5,217.08. So after 6 months, Sam would have $5,217.08. Still not making out terribly if the interest is compounded continuously at 8.5% interest for 6 months. Now let's really go big here. Let's say he doesn't need the money right away. He's just trying to invest and really set himself aside a small fortune. So Sam deposits $5,000 into an account with 8.5% interest for 5 years, compounding continuously. Find the amount of money Sam has after 5 years. So the amount he's going to have, of course, A, equals that initial principal, which he invested, of $5,000. Then, of course, you have that E. And then the rate is still 8.5%, so that would be to the 0.085 power times the power. The time is 5 years, so that'll be times 5. And then we can get a decimal approximation. So after 5 years, he'll have $7,647.95 approximately. So if the interest is compounded continuously at a rate of 8.5% for 5 years, after that time, he'll have approximately $7,647.95. So, I mean, it's not the greatest in the world, but it's better than trying to save all that aside yourself, right? You get over 2,600 free dollars. I'd take it. But that's it for this lesson. Next lesson, we're going to go to the inverse of exponential functions, which are called logarithmic functions. We're going to introduce logarithmic functions and notation for them and what they really mean. So I hope everyone has a great day. Take care.